So hi, everyone. Welcome to edition number 6 of our developer community meetings here at Cerebras. I just want to thank everyone for taking time today to join. Today's agenda will very briefly just remind everyone about our discourse page. Justin will talk a little bit about what's new with our recent Cerebras release or for our SDK. And then Andy will take over and talk about our collective communications library. Just a friendly reminder, if you haven't already, to please join our discourse. We're seeing some, a lot of posts, healthy conversations happening there. This is a great way for you to engage with our team and have, some of our engineers come and contribute to some of your questions and help you out. So yeah, definitely sign up for our discourse page if you haven't already. All right, Justin, you want to kick it off?
Yes, thank you, Uday. So we're excited to announce that today we're releasing SDK 051. Some of the features that are new in 051 are listed on the left here. They include a native CentOS 8 package. So if you happen to be running in a CentOS 8 environment, and you can run bare metal against that OS as opposed to using a container. Another very big feature that we're excited to be releasing is a high bandwidth memcopy. This greatly simplifies a lot of the previous host and device memory transactions in I/O that you might have been doing in previous releases. And as part of that, we're supporting large tensors. So you'll be able to stream large tensors onto the fabric from the host. Also, as part of that memcopy, you get faster ELF loading support, both for reading and writing. And we will be providing 2 different examples on how to use memcopy, and they'll be called residual memcopy and stencil memcopy, and those will both be included in our GitHub as well as our documentation page. We've also prepared new CSL features, which are listed here. Some of them include support for enums, support for switch statements, support for runtime structs, color abstractions, task versus color parity, support for compile time strings, and also support for generics. Also in this new release, we have a new feature in the SDK GUI, which you can see on the right side here, which is support for instruction tracing in our timeline. That will be included as part of the wavelet tracing in the timeline, so you can see, for instance, how long a particular instruction took to execute, how long it took for a task to run, when it started and when it ended. So sort of a very typical type of timeline tracing you get for the instructions and the task level information. And last but not least, we, as you have seen and Uday just mentioned, we released our discourse forum. And so you can all use that for asking questions and communicating with other members of the community. So let me know if there are any questions, but with that, I'll hand it off to Andy to talk about our collective communications library.
Any questions? We'll assume none. So hello, everybody. I'm Andy Gill. I work on compilers at Cerebras. I'm in charge of the CSL group, and I've been doing compilers for, well, 40 years, actually, a long, long time, tinkering and hacking with them. So I'm excited to announce and talk about some of the steps we've taken to try and make communication inside the SDK to communicate between PEs a bit easier. Please do interrupt me with questions. I've got the team behind me here who are going to ping me and let me know if somebody's got a question. I'm quite happy with interruptions. Before I was at Cerebras, I was a professor at the University of Kansas for 15 years. So I'm much rather an interactive discussion than just a monologue. I should say here up front, we've released a 0.5.1 today. This is a library that's written on top of 0.5.1. It isn't actually in the bundle, but we can get this to you to use. It's a preview of the capabilities that are available and what 0.5.1 can do. So what we want to do is we want to look at communication best practices. If we look at what CS2 offers, it's sort of by design, by the rules of physics. It's a two-dimensional way of thinking with locality. Things happen on the individual PEs, and these individual PEs talk to their neighbors. There is no concept of global memory. There's no concept of talking to everybody. You talk to your neighbor, and your neighbor talks to your neighbor, and this is the way that that communications happen. I was reminded when preparing this of the short story by John Steinbeck. He talked about the key event happened early on in the story when someone discovered the pearl, and news traveled very quickly through the town. A mystery not easily to be solved, but there was no global communication, there was no radio, and neighbors talking to neighbors effectively managed to spread this message very, very quickly. So what we want to ask is, what are the best practices when doing collective communications? What experiences have we got? What have we built? What are the different tricks for doing things? So I'm going to go back to basics and sort of put on the table what we have in terms of processing elements, how we think about things, go through one sort of direct mechanism of doing things, and then move on to more advanced mechanisms, and then from there talk about a library that uses these advanced mechanisms. So this is a basically layout of a PE. There's communications and there's compute. And we have a router that has 5 different directions that things can move. Things can come from the north, they can go up the north, they can go east, they can go west, they can go south, and they also can go down what we call a ramp. A ramp is to the compute module, which is a sort of classical CPU-like way of doing processing with extra capabilities to do things like access tensors as bulk operations. So there's this mechanism that each router talks to its router to the east, west, north, and south. The communication or the bandwidth between these can be sort of single cycle. Multiple things you can very quickly send large amounts of data locally and thereby get something that acts globally. Wavelets can we call these pieces of data wavelets. Wavelets can come in and they can go straight through. They can go different. They can go down the ramp. You can actually control via the router what happens. So that's the broad picture. Let's go one more specific. You've got this communication. How do you use it? What's the layer above it? How do you give it some meaning? And how do you use it in practice? Well, we have this concept of color, and I like describing the color of a wavelet like a UDP packet or port. If you're implementing something on Unix, you can listen on a particular port, and then you can trigger some work based on when data arrives on that port. What we have is we have 24 routable colors. The colors are used for other things and triggering other things, but there's a set number of colors that you can use. They're basically ports for listening for things, and this router can based on these numbers decide where to send things. So in this example, red comes in, it goes through the router and goes down the ramp. Blue comes in from the north and goes out west, and then green comes up the ramp through the router and goes east. In this illustration, each arrow only has one color, but these are physical connections that can be multiplexed. The next packet coming up might be purple, and a purple might come up here and be configured to go this direction, unlike the blue that's configured to go this direction. Any questions there? I'm determined to get people asking questions, as well as add the chance to take a quick drink of Coke. Yeah, I see a hand raised there.
Yeah, see a hand.
Go ahead.
Hi, I was wondering, so for these data movements, should we be thinking similar to the linear plus constant cost model for time? In terms of, there's some bandwidth, I assume, and so if you have so does it, do you have a model that application developers can keep in mind?
Okay, so
it's like a startup cost and a per word transfer cost for distributed memory systems is.
Yeah, so what's the mental model you want? If I interpret your question correctly, what's your mental model you have when you want to program this and use this?
Right.
There is no startup cost. What happens is each packet or each wavelet travels by itself. It can contain some data, it contains some routing. So a packet is a traditional datum with some extra information about where it's going to get routed. I don't remember the exact number of bits because there's several several caveats that go on there. But basically, you can be talking about going from the compute up the ramp. It takes a small number of cycles, but you can follow right behind it. You can fill the pipeline with data. And then I believe things going from, say, west to east can go through even faster. The ramp itself has some extra logic that we're going to talk about in a bit. And that's the reason why it takes a couple of extra cycles. Yeah, so hope that's answered the question. So a great use of it would be you've got 2K to transfer from a compute module with the memory, and then you send it up and you can transfer something on every single cycle.
Thank you.
Yep. Another question?
Yep, from Alfred.
Yeah, when talking when you said color, you mean physical color, or is color just a representation of information? And if so, how many colors are there?
Okay, so there's in CS2 there are 24 routable colors. You can set them up statically or dynamically. You can at runtime you can change the router and how it acts. Although it is preferable to set it up statically because then you know what you've got. You can sort of set up a substrate that you're acting on. So you can think of this as 24 addressable action ports in the same way as UDP has, I think, 2 to the power 16. This has got 24, much smaller number, but then you can store that number in, in 5 bits as you're transmitting. And the other numbers are used for special operations. The bits aren't wasted. The bits are used to encode other things. And so color doesn't mean, color is just a terminology we use for this particular number that represents part of the message of. So if you have data coming in from 2 different locations, one's representing one type of information, one representing another, you can multiplex them. You can bring them both down the ramp to the compute. But how can you tell what's coming from where? You use the color as a mechanism to distinguish between the two. So you'll switch on that color, or literally you'll say, if it's red, then put it in this queue. If it's green, put it in this queue, please. Does that answer your question?
Yes, I think so. So the colors mix like we normally think of them in physics, or are there any sort of multiplication tables, any rules, or how the colors interact?
So there are a couple of subtleties that I'm not going to get into today that you can actually have colors that you can actually toggle between 2 colors automatically. But for in general, or the common case is that when a packet has been given a color, it will have that color throughout its lifetime. So you can think of it like an IP address as well, a very, very small IP address that's saying, here's how to think of what's happening. So it's only about local transfer of data. So in this case, if you take the green, what you're saying is I'm going to send something out on the green, on the up ramp, it's going to be colored green. And I know because of the way the router is being configured, it's going to go east. And then the next PE over has to be ready to receive something on that path and have a table, a 24 entry table saying, if I get a green piece of data, here's what I'm going to do with it. So it's literally a small routing table.
Thank you.
Yep.
Hey, Sade, back to you.
So quick follow-up question. So supposing we have a pipeline transfer of data in a systolic type algorithm, would it be typical to have two colors and you flip between them? That is, you receive on red, send out on green, receive on green, send out on red, receive on red, send out on green, and so on for odd and even processes?
You've exactly got my slides. My next few slides are talking about exactly that.
Okay.
The answer is yes. That's the sort of the easiest pattern when you want to flow through multiple pieces of data. So yes, it is a common pattern for these sort of restrictions to let things happen. So I think we're collectively got this. Thank you for the questions. I would much rather have questions and.
And 1 second, Andy,
Yep.
just before you carry on, Emin, you provided a comment in the chat. Is that a comment or is that a question that you also were interested in asking Andy?
Yeah, I just wonder how much is expensive than the communication that Andy was talking about. I still remember it kind of 7 cycle from RAM to the router. Router to the router is kind of 1 cycle, but I just want to make sure myself it's correct or not.
Okay, so the specifics of how many cycles things take, I don't actually know. I've not memorized them. I tend to think of it as in, if you're sending just one thing, it's going to take a few cycles to go round. If you're where the usage pattern is, if you're sending a block of data, and then you can set it up to sort of fill the pipeline and things happen quite rapidly. I don't know the specific number. I've been programming this 18 months. I've never actually had to look through that sort of level of detail of numbers. It may be good to have an approximation number in your head, and we'll see what we can do there in terms of providing that.
Okay, thank you.
Thanks. Yeah. Okay, I'm going to jump on to the next slide, and this is the common pattern that gets used when you're trying to communicate between several items. So we have some data here. We follow it through. What's happening? You're coming in the west. You're going down the ramp. You're doing something. You're coming back up the ramp. You're going east. You're crossing the boundary into the next PE. And they're physically adjacent. This is something that doesn't take. There may be a single FIFO here or something. It's a very, very fast link between this router and this router by design. Then you're green, so you go down again, you're coming back up as red, going across through a third router, going down as red, coming back as green, and going out through the east. So you get this what we call a checkerboard pattern. I'm giving things in 1 dimensions because I'm using slides and trying to explain things. This can completely expand into 2 dimensions. If you're going up and down, you'll have a second set of colors that go on. So you end up with a sort of checkerboard style pattern quite quickly. This has the issue that you're then going down the ramp each time. We'll talk about that in a second. But this is useful when you're computing and you want to do something with some data every time round. So how would we express this in CSL? Oops, double press there. Here's a example of programming this particular design pattern. CSL lets you have compute time structures. The way I think of it is CSL runs 3 times. Now, it actually just runs once, but I think of it as doing 3 things. It runs once to figure out layout, that is what's where and how does the routing work. It runs a second time to figure out what individual PEs are programmed and switches are programmed at. And then a third time when it's actually running on the fabric and actually doing an operation, actually running the code. The advantage with having the first 2 and having the compiler actually do some evaluation is you can replace hacky C preprocessing style optimizations and computation and replace it with the language itself. So you can call a CSL function at compile time to compute a route and make things work. So this is the code that actually the compiler runs, and based on PX, where PX is your coordinate in the X direction that you've initialized or grabbed here, and you're deciding I'm doing red or green, and I'm giving it the route 1 or 2, and then 1 or 2 for green and red. So red is route 1, here green is route 1, and then you've specified the routes, and the routes are, this is you programming the router, and what you're saying is that receive from the west, transmit down the ramp, and then receive the ramp and transmit east. So the concept of where you're going is separated from the color itself. So you can program this up relatively directly, and you can use programming idioms to compress this further. Maybe you'll have an array of these structures and an array of colors and index into it modulo 2. Any questions there? And then I'll jump into the sort of pros and cons of what happens there. So, and some of you have seen this before. I'm assuming somebody's monitoring the chat, because I can't see the chat with my both screens full of pictures here. For the checkerboard pattern, this is relatively easy to implement. You can think about it locally. You can think about myself and my neighbors. They have basically a different polarity of color, and this generalizes in 2 dimensions. The cons of this particular pattern is you have to pass through the ramp, both going up and going down, and through the compute module as data flows. This works well if you're trying to do something on every computation, on every PE as you're acting. If you're just trying to transmit data from one side of the fabric to the other, this is not an effective way of making this work. Also, it uses, off the bat, it uses 2 colors, and colors are a finite resource. You want to be careful and strategic about how you use them. Okay, so let's look at some other patterns that are provided inside CSL, and there are more advanced to use but offer different capabilities. We have what we call the filter bus communication pattern. We do need to come up with a sharper name there, but it's literally a bus because there's a connection with one color going across, and it's a filter bus because we're configuring the router and compute to use a filter to decide what's going to happen. So as an example of the way this is set up, it's not actually sending data in 2 different locations. What's happening is inside the router, on the edge of the router, there's a small bit of logic, and it's executing a small program. And it's making a decision based on what's coming in, whether to send it down the ramp or send it to the east. And then the same code's inside here and the same code's inside here. An example of the sort of thing that can be done is you read 10 wavelets. The first 10, sorry about that, the first 10 get sent down the ramp. The next, after that, it then switches and sends everything else east. And then what happens here? Well, nothing arrives till the second 10. So the first 10 have all went down the ramp here. The second 10 arrive here. So maybe you're sending 30 in total. So the next 10 go down here, 10 arrive here. They get sent down the ramp, and any more get sent to the east. So this is a system where you can set up a quite powerful filter that decides how things get directed as you're sending them. Any questions there?
I have a question.
Yeah.
So we use this communication pattern especially for sparse matrix or sparse tensors, right? So we can basically program the router which only gets non-zeros, or we can distribute it like non-zeros, different PEs. We can use.
No, this is not about sparseness, although you can absolutely use it for this. We have various mechanisms for. I didn't talk about them in this presentation, but we could talk separately about that. When there's there's automatic mechanism for optimizing over sparseness, and you do compute on the interesting data, not the passive data. In this case, it's you are statically deciding, am I going to do this? I'm going to send it down a ramp, or I'm going to send it east, just by having a counter. So it's used for a different part of the design space of sending data.
Okay, thank you.
And there was a hand raised there.
So I was wondering, what's the API from the CSL programmer for this?
Again, there's you're one step ahead of me here. So so I'm going to jump to the punchline. The punchline is this is tricky to program. We in CSL are provided access, almost direct access to the hardware APIs that the kernel writers and programmers wanted to be able to use this particular idiom effectively. There's some code here, and I'm not going through the specifics of what these all do. It's just meant to sort of illustrate what's going on, but these are all individually addressable parts of this small domain-specific language for programming filters. You can program at this level. People do program in this level, but it is, you have to orchestrate very, very carefully how each filter works. And then you also have to think about what happens in terms of, well, when that data is all finished, can you send another set of data? How do you reset back to a particular place? You also have to think about, you know, if someone else is using the color for something else, there are just lots of considerations. You also got to be careful about the terminal at the ends and how that might act slightly differently. So there are lots of considerations. So this is challenging to program, and I've done some programming with this myself, and it is quite easy to get lost in the details of what's happening here. Question?
So I assume this is going to be the best way to do a broadcast along a direction, so that you don't have to go in and out of the ramp from the processor, but you can just stream. This is a common pattern that will be important for
Exactly.
multiplication, for example.
Yes, if you're trying to do some sort of broadcast or some sort of scatter of data, this is a mechanism to use. However, this is a low-level API. And what I'm going to talk about later in 2 or 3 slides is I'm going to switch to talking about a library that we've written to make this easier.
Okay, great. Thank you.
Yep. And the library, the only way that a mechanism by which the library makes sense is that we see how involved it is right now. So this is one direction. This is us getting data. You're coming down a particular route, and you're then broadcasting data to lots of people. There's a counter which is called a switch. When you've got again in the router, or sort of between the compute and the router, you've got some logic that decides how I'm going to do routing and how I'm going to switch between routing. So in this particular picture, we've set up this router, so all it does is switch through. The data comes up here, goes to the router, and goes here. That was trivial, that was set, that's the edge condition. But then here, we've got data coming in here, and we've got data coming up the ramp. So how do we decide what to do? So one of the models is we accept a certain number of packets from the west, and then we switch to receiving packets from the ramp and send them both east. So we can dynamically switch based on conditions who we're listening to. So both of these are red, and this one disables and this one enables after things switch. And then you've got ways of sort of carrying on toggling. And there's up to 4 different modes. So you can actually have a system where you're listening on all 4 directions to do particular things. So you can switch between 2, 3, and 4 different things. So at this point, 10 things have gone through, and then the switch toggles, you're sending another value up. Then the switch here, you get the same model again. What you're doing is you're sending through the first 20, and then the switch happens, and then the last 30 arrive. So it's the counter to the one we had earlier when we were broadcasting. Now we're gathering information. And again, here's a picture of sort of what happens is that it was defaulting, and this isn't code that implements the previous page, it's just representative code of what it looks like. You're saying maybe it was transmitting to the west before, and you're switching to transmit from the east under a particular condition. There are packets that we can send that actually are control packets rather than data packets that can trigger these things. there's ring mode, and the current switch position is 1. So you've got basically clock arithmetic or modular arithmetic in the way you're acting here. So
Hey,
again, small
hey, Andy?
DSL. Yeah, go ahead.
Looks like you have a few questions in the chat.
Yeah, please do read them.
Yep. So from Mia, does the filters require the latest SDK, the 0.5.1?
Yes.
Okay.
They may be there in 0.4. We've actually changed the syntax and the way you access them to call out switches. And if I go back to slide, call out filter. So we've made it more modular in terms of how you use them at this point. So, but yes, it does require that. I would certainly switch to the latest, pun not intended. I would certainly move to the latest version.
Great. And then Luke has a question. Is this CE inject? And Luke, if I did not correctly articulate your question, feel free to hop on.
Is this CE inject? No, I think it's CE. So the truthful answer is I don't know. I don't think so. I think CE inject is another sort of similar mechanism by which you can trigger particular control patterns rather than data. So I think this is an orthogonal mechanism, but I mean I could be wrong. So I'll actually check into that. I've never written a CE inject program myself.
Yeah, this is different from CE inject, just to clarify. Yeah.
Well, yeah, thank you. Yes, I think I know what CE inject does, but I've never actually used it. So this is part of the challenge with with this language, is we provide almost direct access to all these hardware features, but there's lots of them. So there is quite a lot of learning to get up to speed, and that's what we're trying to provide abstractions so that not everyone needs to go down to this level. Any more questions in the chat?
Yep, we have one more from Alfred. Since the processors can talk to their neighbors around them, colors is just a way to program a route map for data flow. Is this correct?
Absolutely, 100% correct. Yes, that's a good way of putting it. Yeah.
Awesome, and that was the last question.
Okay,
you can
good.
Continue, Andy.
Good. So
then why is 24 colors enough?
So why is 24 colors enough? Well, 24 colors is what you've got, but that's quite a flippant answer. The 24 colors is what you've got locally. So your neighbor can have a different set of 24, and your neighbor next to them is 24. The colors have to match when you're sending data and you're talking, two neighbors are talking. So something that's got color 14 will be received as color 14. The challenge is then what happens if you want to have a pattern so that I can send something to my neighbor and then I pass through to my neighbor's neighbor and then I pass through to my neighbor's neighbor's neighbor. Quickly you start running out of colors. You don't have enough to do complicated patterns. If you want to be able to send something to 8 different neighbors, then how many colors does that take? Because you've got to have toggles and different things going on. And then you want to act in 2 dimensions, so you've suddenly sort of doubled it or quadrupled it, depending how you do things. Our experience is you can do a lot with 24. It's certainly a precious resource that you have to carefully decide when you use it. A decision is not once and for all time. Once data has flowed down, you can reuse that color for something else. We have a mechanism by which you can actually reprogram. You can detect things have happened, and then you can reuse that color later. So you can have like almost modal executions. I hope that answered the question. Yeah, okay.
It did, and then we had a follow-up comment from Sade. Having more than 4 colors makes it convenient to use different colors for different arrays that to have to be communicated between processors.
Yes. So if I go to this picture, let me find a picture here to talk. If I had 2 arrays A and B here, and I wanted to send them here, I could set up 2 colors, green and purple, and then I could receive them here and set them up so I listen in green and listen in purple to make that work. However, the reality is that you can't send 2 things at the same time. So how I would have programmed it was send something up green, and then immediately afterwards send the secondary up green, and then receive it in that particular order. And things won't go out of sync. The packets are completely reliable. So yes, you could use colors for that, different colors for that. In reality, you tend to use things over time because the bandwidth is limited by how many things you're sending over that edge here. Okay, if there's no more questions, I'm going to jump to, these were great questions. Thank you for the discussion and questions. Let's look at the collective communication library that we're working on. If we look at the 4 principal things you can do in a collective communication library, and you can think of this as sort of MPI light. And I'm working here in 1 dimension intentionally. The library works in 2 dimensions, but the operations are all at the moment 1-dimensional. If you want to do something in 2 dimensions, you can trivially stack 2 of these together to get the behavior you want. And there are 4 types of collective communication. The first one's broadcast. When you've got an array A, B, C, D, you've got 4 items and you want to send it to 4 PEs. So you send the same thing to 4 PEs. Now, obviously, sending it to yourself is trivial. So you're sending it the same thing to 3 different people. This need not be the first one. It could be over here. It could be any place on this row. We could send it from anywhere. It's completely configurable. It's there. And then you've got scatter. Now, scatter is when you've got 4 things. You're sending to 4 arrays. So I'm sending A to the first one, B to the second one, C to the last one, C to the second last one, D to the last one. Now, broadcast, if you've got broadcast, you can build scatter because you just broadcast everything everywhere and then you just select the correct one. But you could imagine scatter being more efficient because here, rather than having to transmit everything everywhere, here you're only transmitting individual pieces. So you only need to send D down this particular path here. Taking things the other way, when you're pulling things together, you've got gather. What gather does is it takes individual pieces of data and joins them together on a particular location. And then reduce. Now, what reduce does is it does the same as gather, but also does a mathematical operation on the data. So in this particular example, we take 1, 2, 3, 4, and we add them together and we get 10. There are reasons why that might actually be better because we can imagine using sort of log tree type approaches to do things. So you could have a situation where the addition's done on the fly as you go along, or you could do a gather, pull everything together, and then reduce. You could even reduce it as data is flowing in. There's several different ways of doing this, and so this trade-off's exposed in these 4 operations. So we've written a library that provides these 4 operations. Let's look at scatter, and then let's look at gather. And I'm just going to focus on the particular code. I'm going to try bring up some code and see how that works to make things work. So if you're sending data to many locations, you've got a set of data. So if you've got n PEs and you've got an n by m matrix, so 4 PEs, you've got 10 items. So you've got an array of 40 things. You want to have 10 things arrive on 4 PEs. So we're sticking with 1-dimensional and we're sticking actually with 8 PEs in the example. So I'll see if this works here. Bring this across. So here's a library for doing this. And this is actual code. This is code that we have running. What we've set up here is, if we look at the program, is we've got 3 different colors and tasks. We have an initialization task, we have a scatter task, and we have a compute task. The compute doesn't do anything, but it sort of shows that the linearity is being maintained. We start the initialize. We start the init color. That is, we actually start this code here. And what we're doing is we're just filling the source with I times I. So we end up with 0, 0, 1, etc. The square numbers all the way up, 1, 4, 9, 16, etc. And then once we've done that, we activate the scatter code. What the scatter code then does is it initialize the connection between the 8 PEs. We then do the scatter itself, and what information do we need to do this? This is a single call. Is we need to know which the location of the data we want to read, the address of the data we want to read, the address on every PE. It's different on different PEs of the destination, how big the destination is, so how we're chunking up the data, and then where do we go when we're done? So once we've finished receiving all the data, sending and receiving all the data, we then trigger a color, and then we go to, and we can now do some compute with DEST. And I'm assuming some familiarity with CSL here in terms of this is a real program. We have the source here, which was P long. On this particular example, we're using just 1 by P. And we've got our destination, which is just 1 long array. So we've got 8 things, and we're scattering them to 8 different locations, each array being 1. And as you can see, this isn't too long. This is some extra code going around it to set things up and do things afterwards. But in 50 lines, we've managed to do this by pulling in what are here are libraries to make things work. We have some common code and some code because we're acting in the X direction. There's also an equivalent library in the Y. And then just to show the code to pull things together, when you pull things together, you have some initialization you do before you call the code to set the to call the specific PE code. So I'm going to jump back to here and ask, are there any questions? I see some in the chat, but I can't see the chat itself.
No, these are all previous questions.
Okay. Okay. So I'm hoping this seems simpler than trying to work with filters and switches. One of our engineers has done the hard work behind the scenes to make this robust and make this efficient and sort of make good uses of things. You will always eke out more performance if you go down to the lowest level and you sync everything up and make it work. There are lots of places to do things. However, the intent here is you can have something that's performant and easier to use, and it's linear in the sense of you finish the transmission, now you can go off and now you can do the next stage. You've got a continuation color, technical term, that lets you know that when that's triggered, I can now go to the next point. I should say we use colors both for routing and for synchronization. They act broadly like locks or multixes. So no questions there?
We have a question. It says, can
Yeah.
you say something about performance, theoretical versus sustained?
It's a good question. So there's I don't have in front of me the actual performance numbers of the library as it stands right now. I know that considerable work was put into it to make it as performant as we could squeeze. It's not a naive implementation. It does use the broadcast mechanisms that we've got to make things work. So I believe it is making good use of the hardware, but I don't know if its exact performance numbers. That's something that if someone's got the library, they could measure themselves. I do know we did considerable profiling and measurement at the time it was written, so I have confidence that it's doing a reasonable job. Any other questions?
Nope.
Good.
Carry on, Andy.
So we've got gather. This is the other way around. It's taking in the case we want to do, we're going to take 8 PEs and pull it in and make that work. So let's go to here. In this case, it's the other way around. We have an array of 1 element spread over 8 locations, and we're trying to gather it together to be on 1 array of 8 elements. And how does it happen this time? We have the same initialization pattern, and then we gather. We call gather, similar sort of arguments, a very similar shape. And then after we've gathered all this information, we have a continuation color, so we can trigger the lock that allows this compute task to use this data. So again, the same shape, again the same idea. They all have this sort of flavor inside this space.
Hey, Andy, we have one more question from Emin. Just for confirmation, communication is 1D, right? We need to explicitly code it for 2D?
Yes, the library as it stands right now, and we are looking to see if there's a good idiom for 2 dimensions. We have written 2-dimensional examples, but if you broadcast across a row and then you run the same program on every column that broadcasts over that column, you've done the effect of broadcasting in 2 dimensions. So we'll look at the library and see, is there a value added by providing an extra function to do that? Or is it so straightforward that it's not worth us complicating the API by providing that? Any other questions?
Sade is asking, will these example codes be available to study in depth later?
Yes. Yeah, I've got in this code here, we can certainly, I don't see why we can't make it available. It's just a usage of the APIs that we're building up. And we want to wrap up this particular library. It is written in and works on 0.5.1. So there's no features or functionality it's using that you don't already have access to.
Thanks, Andy.
Yeah, so we just got a final slide, but one of the sort of, and if this has made sense, this will be relatively obvious or straightforward. The checkerboard pattern works well when you're processing data in motion. So you're doing something and you're adding and adding and adding, or you're somehow changing the data as it's moving down a pipeline. The checkerboard pattern works quite well for that. The bus design works better if you're sharing structures and then acting on mass and then bringing things back together. But nothing is mandated. These are just libraries, these are just usage. There's no reason why you can't use both patterns in the same program at different times. It's not a switch or a mode. It's just a way that you utilize the colors and set things up. Last questions. We're at time. So any last questions and any sort of feedback of that looks useful, or have you considered adding this? These are the sort of I'll switch over to the roundtable discussion now, I think.
So Andy, Luke has a question. Can we dynamically adjust the size for these operations at runtime?
Good question. I do not know the answer to that. There is no reason fundamentally you couldn't. The library may not support that. I haven't looked at that. That's a good question. But anything that you can configure, you can configure everything or almost everything at runtime anyway. So it should be possible to have a version of this that's dynamic. I think it's static right now.
That was the last question for now.
Okay. Okay, Udi, I will hand back to you here to take this.
Yeah, I'll ask a open question to the audience. Based on what Andy shared today, are there any feature requests, or is there anything in addition to what he shared that you'd be interested in? Okay, so Michael says, this all looks great. In addition to collective operations, our group will be interested in stencil communications. And I think this gives us some good ideas to work from.
yes, the how can I put it? An obvious extension would be have a stencil pattern as a library that you could then instantiate. So you could have a 7x7 or a 3x3 stencil that you could factor out the code that does the communications from the computation. That's not something this supports, but that's a good thing for us to consider.
Yeah. Oh, Emin, I'm really interested if we can have some profiling tools for real machines, something like Insight at NVIDIA.
Yeah, I can respond to that. So the profiling tools are certainly something that we are thinking about, and yeah, it's actively being worked on.
And Michael says we'd be glad to contribute back anything we're able to develop on our own. Thank you, Michael. That'd be awesome.
So I have a question for Justin. So the time trace tool that you mentioned in the beginning, is that going to help with trying to understand what's happening with a?
Yeah, so I should clarify, profiling on a real hardware is, you can essentially derive the same information from profiling and simulation. And so we have pretty much most of the tools you would need to get the information that you want for profiling code. An example of that being the instruction trace released in O.5.1, where you can profile when a task started versus when it ended. There should be no performance differential when you move from simulation to hardware. So in fact, I would suggest doing most of your debugging and profiling in simulation.
Thanks.
We could use this as an open floor for anyone else on the call that wants to share a question, comment, or like a feature request.
Yep, and by the way, we are happy to talk to any of our users at any point in time if you have any features or very specific points of feedback. And so you can all use that developer@cerebras.net email or our discourse forum, or we can always set up some time to talk one-on-one with you.
I see a hand raised. Mia, would you like to ask you a question?
Yes, hello, I'm Mia from Japan, and I measured some bandwidth of the HPEs, and I got some weird numbers. So my background is HPC, and I tried to mimic the stream benchmark, which is most famous benchmark in HPC area. And I would like to ask the performance which I measured before on real machine, but how do I do that? First question. I would like to discuss my measured performance.
So the question is, how do you measure performance on a Cerebras machine?
I measured the basically I got with the times libraries to measure the performance. I mean cycles.
So if I'm understanding that correctly, it's how do you measure the number of cycles that any task or anything running on the hardware might take?
Okay, let me check it.
If anybody else has a response, please go ahead.
Actually, sorry to interrupt, Justin. So actually, like I would like to say that on the like simulator stuck a lot. I just post on this course. Like even if some small numbers, if the metadata is huge, which means like simulator cannot process the metadata and visualizer and profiler on the simulator cannot work properly. That's why we have a problem right now to profile even on the simulator. If we're able to simulate something like for the big input case on the simulator, that would be enough for us for right now. But there's kind of the problem on the simulator, which cannot process large metadata, which means when I use kind of lot in input size, it's actually not that large. There are like even I'm doing kind of multiplication. I'm using like like 36 by 36 or like around 50 by 50, which when I get when simulator result ends, I cannot use profiler to profile effectively, get the cycle information. It's stuck. I mean, it's hanging. So that's the problem that I posted on this course. The answer I received, it says is expected, which means there's a bug on profiler right now for the simulator case. I wish it would be resolved as soon as possible.
Yes, thank you. So doing large scale simulations is going to be a very clear challenge. Generally, what happens is when you're developing, you're doing smaller scale simulations, maybe hundreds of PEs or smaller tensor sizes, and then once you want to scale up, you move on to hardware. And so we're actively addressing the ability to do larger scale simulations, although obviously that will always be a challenge. It's hard to simulate almost 1 million PEs in software, and so keep posted. We're going to be releasing features to do larger scale simulations, but also if you are interested in running on hardware, or you've come to a point where it's becoming a limitation, feel free to reach out to our team, and they work with you to either run on hardware or resolve maybe some of the issues that you're experiencing.
Okay, thank you.
Yeah, and if anybody has any questions, I know we had one question that maybe I wasn't able to answer. Please just message us at our email or on our discourse forum, and we can communicate with you there. But I think we might be a little over time right now.
Yeah, it sounds like these are some of the issues. It's best stepping through concrete examples, and that way we can make more rapid progress.
Definitely, yeah.
Great. Any last questions before we conclude this meeting? All right. Well, thanks everyone for joining, and thanks for a very engaging meeting today. This was great. A lot of discussions, which is awesome. Yeah, just to reiterate what Justin said, if there are lingering questions or questions that you want to go deeper in discussion with us, please use our developer@cerebras.net email or use our discourse forum to reach out to us, and we'll be happy to go deep on any of these topics with you. Yeah, thanks everyone for joining, and we hopefully will see you next time.
Thanks.
And thanks, Andy, for presenting today. Appreciate it.
Absolutely. Thanks, everyone.
Thanks, all.